here today. We are Spark Cognition. We are local Austinites based just down the road from NI. And we are going to talk today about machine learning. My name is Sumant, and with me is my colleague Keith Moore. So just a quick show of hands, how many of you here are aware of machine learning? Just heard of it? Okay, that's good. So I would say about 50-50. So that's a good mix. We want to introduce machine learning. We'll go a little deep into some of the concepts, but we'll talk more about the applications and how we think it has the potential to really change things. So we'll learn about how machine learning is revolutionizing prognostics of machines. We'll learn about Spark Cognition's unique approach to cognitive computing, which is a way of getting machines to work and think like human beings. We'll talk about a couple of real-world examples, and we'll talk about how our predictive analytics integrate with NI tools. And if we have time, we'll go a little deeper into different aspects of machine learning. We'll make sure we have enough time for questions at the end. So, very quickly, I recently read a Reddit transcript of Bill Gates' conversation where he was answering to any questions that people posted to him online. And one question was, if you could go back in time to when you were back in college and you could do things differently, what would be those 3 things? And of the 3 things he mentioned, only one was regarding his professional work. And he mentioned, I would have really kept a closer eye on and concentrated more on machine learning. So we think he was absolutely right on that one. He also said at one time that machine learning, a key breakthrough in machine learning is probably going to be worth 10 Microsofts. There we think Bill Gates is probably wrong because he is really underestimating the effect that machine learning can have on the world. So what are the benefits of machine learning over and above conditioning monitoring or normal statistics? So the first one, and I want to make sure I cover this one in a little more detail even at the outset, is automated model building. What does automated model building mean? It means that when you have an asset, when you have a new asset, you don't have to start from scratch building the model. You don't have to worry about every last physical variable, what kind of sensors you have, what's related to what. And then when you have a new asset, you don't have to start the whole process over again. It's a part where we have the right algorithms which can have an ensemble of models and choose the right one which will give you the best results. And models can be both supervised learning and unsupervised learning. We'll cover some of that. But the key here is it's automated, it's fast, it's highly scalable. Deeper insights. That's where I think where cognitive computing really makes a difference. Machines are really good at logic, but humans are better in some cases for pattern recognition. We can detect a deviation in pattern better than a machine's logic, or being able to program that machine's logic to detect the same deviation in the pattern. And that's where cognitive computing comes in. It can go in, it can understand patterns, it can hunt for them, not only at the first order, but in nth order, trying out very different relationships between the variables that you have in the data, and hunt those patterns and then use them to our advantage, which most frequently is to predict failures in critical missions. There's adaptability and ease of management. There's security in terms of machines don't care exactly what is driving the difference in performance. Is the difference in performance because wear and tear? Is it somebody's malicious intent because of the intertwining of IoT and the internet as we knew of 5 years ago? Is it because of that the performance is dipping? Machine learning can read both at the same time. Let's go to the next slide. Here I want to just talk about the three buckets which I can use to describe cognitive. One is continuous value prediction. So this is about understanding what state a machine is in. And I'm just using machine here as a substitute. It's basically what state is a system. And understanding what is the entire sample space of the states that system can be in, and then making a determination as to what state the machine is in currently. It's an optimal state, suboptimal state, failure, leading towards failure. Then it branches into classification, which is basically trying to get these states. Many times, operators know these states. They know that this is when it's normal operating conditions. This is where it's failure. But this problem, it might seem easy at face value, but it's not. It's very easy to classify normal, but it's the boundary between normal and failure or tending to failure that's very difficult to understand how it works consistently, and to be able to detect the transition from one to the other. And the last one is natural language processing, NLP. This is the ability to talk to a machine as if it were human. A prime example of that which we work with is IBM Watson. So Watson can learn a lot about your machines, reading all the documents that you have. Watson can talk to your experts, because the experts can provide feedback to Watson on exactly how it's doing. Is it getting the right answer? Is it getting close to the wrong answer? Or is it completely off? And Watson keeps learning. And in effect, Watson becomes your go-to guy in your company, who is basically augmenting the experts. So when customers call, or when technicians on the factory floor are looking to understand what is happening, what they should do, they don't have to go to an expert directly. They can talk to Watson, figure out what's happening. They can read documents if they still want to, but they don't have to bring in an expert for every single problem. And machine learning and cognitive computing can really help you leverage the data that you have, or the sensor chains that you are running to the fullest. You can start with understanding your states. You can start with understanding when states change, when they go towards failure, being able to predict them, all the way to remedying the problem. So asking Watson what exactly happened, having a process flow which allows Watson to give you an answer, for you to execute on an answer, or talk to Watson more about what else needs to be done. But basically, from machine state to encountering a problem, so this slide on the right-hand side, it talks about the market. So we know that the market for machine conditioning monitoring and predictive maintenance, that's a much bigger market. But even that is growing at a very fast rate. An MIT study found that 240 billion is lost in the US every year just due to bearing failures. Bearing failures is important because we see it consistently as a root cause of failures in rotating machinery that we get. But it's not just that machine learning can be only applied to condition monitoring or to rotating equipment. It can be applied across the board. And I'll talk about healthcare in particular. When I was in graduate school, I did a project for a non-profit hospital in South India, and I spent 3 weeks there working with the folks on the ground. When I was there, I met a bunch of surgeons from all over the world, from United States, Canada, Germany, all over the Western world, who had come there to do 2-month stints. And till that point, I was aware of doctors coming from places like India, places like the US, to learn about advanced medicine. But the first time I was exposed to something in the other direction. So I asked them, why are you guys here for this? And the answer they mentioned surprised me. They said, in 2 months, I can do as many surgeries here as I can do in 4 or 5 years of medical school and whatever follows after back then. So what that tells me is, in the healthcare field, doctors really need to see a lot of things. And one doctor cannot basically see all the things working at the pace, for example, that they work in the Western world. Now, that doesn't mean that this problem can only be solved by setting all doctors for 2 months to a year. We think, and Watson has actually proved it, working with premier medical institutes, that you can actually use the knowledge of all doctors everywhere, or actually, or at least a big sample of them, get that knowledge in, and then being able to see, okay, I see symptom X, symptom Y, and something else is happening. I have not seen it before. The literature points to multiple things. What could it be? And Watson can actually tell you, okay, it's most likely Kawasaki's disease, or something tropical, or something that is exotic, which is not usually seen in a place like that. So that to me really speaks to the power of machine. So next I'll talk about where we focus on. So we saw that machine learning can be applied across the board. Where we are focused on are primarily in energy and what I would say are the adjacent verticals. Manufacturing, again, employs a lot of rotating, same for transportation, and in cloud security. There are a bunch of other verticals that use and can use machine learning and really leverage it. But it's just that this is where we think the data is right now ahead of the application. That's where we think that we can actually take the data that is available and bring it the insights that can actually be squeezed out. If you can see on the right-hand side, our customer list is very impressive. We have been out for about a year now. We have 25 clients. A majority of them are Fortune 250 clients, and we have been able to drive concepts and pilots to those clients. And they range, a big majority is in the verticals I mentioned, but we also are seeing traction in areas such as retail. We also have very strong partnerships in place with players such as National Instruments. It's a very natural combination for us, from going from sensors to the analytics. And in the same vein, we have key partnerships in place with IBM on the Watson side, the software side, which is the cloud offering, and also the HP.
All right. So I'm gonna take over here for a second, guys. Again, my name is Keith Moore, and I had a lot of coffee at lunch, so please bear with me. I'm pretty high energy most of the time. So Sumant's done a good job of kind of lining up what machine learning is and how it can be applied to different industries, what it does. I'm going to try and take you through what Spark Cognition does, and why we really can improve how you go about condition monitoring, and really what machine learning in general can bring to the condition monitoring field. So, hit it. All right, so let's start with the what. What do we actually bring? The product I want to talk about is Spark Predict. So it's our physical asset failure detection and prediction program. What it does is it's going to take a bunch of sensor data. So it's going to take it from your existing data acquisition system, for example, InsightCM, because our National Instruments partnership is one of our flagship examples. It's going to take all that data and build a bunch of models from it. So it's going to automatically build models. From those models, it will identify anomalies. So what's going on in the data? What are the trends? What are the patterns? What can we actually do with it? It does all of this automatically. It's a really low-touch item. So at that point, you can take these models, you can take kind of what it flags as anomalies and bring it to your technician or a vibration analyst, and you could say, hey, what's going on here? And he'd look at it and say, oh yeah, that's definitely a failure on an exhaust bearing. At which point, you train the machine on that, and the next time that exact same anomaly signature shows up, instead of saying it's an anomaly, it's going to say there's a failure on the exhaust bearing. So that's kind of part of what machine learning brings. It also, so in parallel with that, so besides identifying what failures are, teaching you so remedially how to fix them, it will also walk through and figure out where there are potential failures that could occur. So it's going to identify kind of a risk analysis per asset and give you a probability of how at risk that asset is. So that was the what, here's the where. Where do we actually sit? How do we integrate? In your system, you're going to have a ton of different assets that you're monitoring. Condition monitoring you don't do for just one or two things. It's generally a large fleet you're working with. So you have all your assets, all of your data acquisition systems, so your sensors running through your compact Rios, and running all piping back down to InsightCM or whatever data historian you guys decide to use. Where we work is on top of that data historian InsightCM, so kind of where all of the data convenes. At that point, we do not replace the system. We are an augmentation of the system that provides advanced analytics and predictive capabilities. So we can help you with your asset monitoring, give you some actionable insights, so something that, say, your vibration analysts see and would recognize and prioritize. And we can also help you optimize everything throughout a whole system. All right, you guys with me? So that was the what and the where. I think it's also important to try and cover some of the how. So machine learning is to some degree still a fancy black box that spits out magic. So I'm going to walk you through one of our algorithms, the Spark Pythia algorithm, at a really high level and explain what's going on underneath the hood. Again, high level. So I'm an engineer, not a data scientist. We have a team of PhDs for data science, and they are very good at their jobs. So you're going to have a bunch of data that you're taking in. So from a cloud, from a sensor, wirelessly, it's all coming into one place. So Spark Pythia is going to take all that data from that one place, and it's going to straighten it out to where everything can be read in its one giant, massive data. At which point, it's going to cleanse that data. So when I say cleanse that data, it's going to recognize which data is relevant for identifying anomalies. So when we're talking about, say, monitoring a turbine, say you have a photo sensor out there. So this just tells you what the light levels are. That probably is not going to be a great indicator of if that turbine is going to fail or not. So what this step's going to do is actually automatically clean out everything that is not correlated to anomalies. Next, there's a relatively complex item that occurs called neural networks. So we're going to spawn a huge ensemble of neural networks, and this is a complex data science tool, and try and figure out what the best models should be for actually predicting how this data behaves. So this is going to be different for every single system it's plugged into. Once we spawn those neural networks, it's going to go through each one and figure out how accurate it actually is. So run the data back through that you've tested and figure out the level of accuracy. Once it's figured out how accurate each neural network is, it's going to actually balance out the top performers and figure out how they balance together to create the most accurate model for your system. And as you continue to add data into this system, it's actually going to constantly relearn. So this is a constantly changing process. This is the machine learning that comes into play. Finally, once you actually are continuously learning, you're going to get your model, and it's going to be able to tell you what the likelihood of failure is per asset, per event. And then finally, you'll notice, back 1 second. You notice I've highlighted some things in blue over here. So everything you see highlighted in blue is actually patent pending by Spark Cognition. So these are things that we have done in a custom fashion for this field. So this is really the level of innovation we bring to the table that you're not going to get with most machine learning companies or really predictive analytics companies in this domain. So that was the Spark Pythia algorithm. We'll let Sumant take a second and tell you about how it was used for the IEEE competition.
Sure. So we'll let Keith catch his breath after that slide. On this slide, what I want to talk to is that we are bringing something new. It's not that we are the only company necessarily doing it. We think we are the only one doing it in a particular way, as was indicated by one of the earlier slides. But our customers expect a lot out of us. Our partners expect a lot out of us, and they put us to tests, which we are happy to submit ourselves. One of them was a test that NI brought to us, which was looking at IEEE PHM data challenge from 2012. And the PHM data challenge is an open challenge where there's a bunch of data that everybody has access to. You can go ahead, you can crunch the data, and in the end, what is expected is an outcome which is in most ways predicted. In 2012, there was a testing set and there was a training set. The training set consisted of bearing data, and it pointed out exactly which bearings failed when. And in the testing set, what you had to do was, the test was till the current time or whatever the current time is, and you had to predict which of these bearings were going to fail. So it was a very real world test. The winners of the test, and there's both industrial research groups and academic groups both participate in this exercise. The winner was a group from a multidisciplinary center in a premier research university in the US. And the method, and it was made up of computer scientists, mechanical engineers, and electrical engineers. And their winning solution, very powerful, depended on analyzing the data, understanding it, trying to classify what are the different families of bearings manually, trying to identify exactly when a hairline fracture appeared on the bearing, at what rate it then proceeded to expand, and at what time it did. So using that approach, they were able to do that manually and get good results. we used our algorithms, including Spark here, which we've just discussed, and we were able to do this in a very automated fashion. We threw the data at it, we let it learn from the failures, we let it build the signatures that it needs to build in order to understand what a failure and just before a failure looks like, and then we gave it our prediction. And our predictions were, in some cases, better, and in other cases, on par with what the best human team could get. So that just shows you that machine learning can really augment what human beings can do today. So that way, human beings can really focus on what are the really tough problems, where you need things beyond data, intuition, to get here. And we'll talk about those in our real world cases.
All right, so I'm going to jump back in. So what we've been doing, so our algorithms are very innovative. What we've done with the IEEE data was phenomenal as well, particularly how we did it in automated fashion. We've been garnering a bit of recognition elsewhere as well. You can see Dr. T has called out how excited he is for what we do for big data. Mark Haney, the CTO of ExamSoft, believes that we have a really innovative framework that can be leveraged in the security space as well. We've been called out by IBM, we've been called out by Gartner, the top research firm, as a cool vendor of 2015. And that's really just the tip of the iceberg. We've been written about in Forbes and numerous other articles, numerous other big publications, as one of the new big data, machine learning, cognitive computing companies to know. So let's talk about outside of the tangible benefits we bring with extremely complex algorithms, what other benefits you get from a machine learning system delivered by Spark Cognition. So if you were to look at the first thing, we're data agnostic. So I've talked a lot about turbines, but our algorithms are not limited to turbines. They are not data specific. They will take just about any type of data inputs and use them to actually generate predictions for different assets. So say you use pumps or windmills, whatever it may be, we can work with that. Secondarily, we really respect data privacy. The data that you guys are actually using is your data to keep. We're going to so use our algorithms, build a bunch of models on top of them from your data, and you can use those for improved productivity. There's the word. But the models and the data are going to be yours. We're not going to take them, we're not going to turn them around and use them for other customers. So that is your IP. It's something that we will not touch. Finally, we're platform agnostic. When I say platform agnostic, I mean security is a big issue these days. So a lot of people are uncomfortable deploying a large-scale machine learning analytics platform on the cloud. So that way the cloud has access to whatever their data is coming from. Because of that, we are comfortable doing cloud-based deployments of our systems as well as on-premises-based deployments, whatever fits your application the best.
And I just want to underline Keith's point about data privacy. We don't make any hardware, so we are not attached to any hardware. We don't come built into any hardware. The advantage now is that we can work with any hardware that we have. But when we deploy our algorithms and build the models, those models are flawed. And in today's world, data is a competitive advantage. The models that you build from the data is a competitive advantage. The insights you get from those models is a competitive advantage. And once we are deployed, the data, the model, the insights all stay behind your fence. We don't have any access to it unless you need us to come in and do something. So that's just a point I want to stress.
So piggybacking on the deployment side of things, what would an actual deployment with us look like? So what we've kind of spoken about is a relatively large, complex, scary sounding thing, at least it was to me when I first heard about it. But realistically, we've broken it down into a pretty simple three-phase process. So phase number one, you have a proof of concept. This is just a few weeks of looking at the data and seeing how our algorithms treat your data. Secondarily is when you move into scaling, so you take that data, instead of taking a few different files, you can actually live stream data. And then finally, that's when we move into the in-context remediation, so the integration with Watson, taking existing assets that you guys have or existing documentation and making sure that our system is up and running with that as well.
Okay, so with that, let's get into the customer case studies. This is where really the floor hits the road. The first one we'll talk about is a leading utility. Actually, this is the work we did for Duke Energy, and I'll just take 30 seconds more about it. We have been working with them for the past few months, and I think it's been a really exciting project for us. It's underlined that Duke Energy is not only one of the biggest utilities out there, it's not only one of the most successful utilities out there, but that the culture of innovation is alive and strong. And I just want to thank Bernie, Brian, Terry for your sponsorship and your support as we embark on this partnership. So the business problem here is to analyze transient events for combustion turbines. Now these in most cases were turbines which were deployed during peak loads. Current analytics are not cannot analyze transient events that well. They can do well with steady state transients. Historical transient events that are anomalous have not been labeled. They might have been seen by certain people, but they are not always labeled by, okay, this is exactly what happened. And the knowledge around event analysis is held within the key of vibration analysis. Furthermore, the waveform data sets are very large. As transient events are not that long in time, the data collected is at a very granular level, and that's where the analysis is done, and it's a very big data set. There's no common baseline for the team to talk to say, okay, this is what the baseline looks like, and hence so and so is the deviation. And analyzing how a specific asset degrades over time is not straightforward. In some cases it can be covered by a particular analyst's experience with particular assets. So the results. So what we were able to do with the data set that we have is we were able to identify anomalies without training by experts. So this is unsupervised learning. Of course, we welcome SME input wherever we can get it, and we have been working closely with the group at LabVIEW who are there to guide us along the way. With their help, we were able to understand exactly what some of the incomplete events look like wash events or aborted startup events, and we were able to find the signatures for those events and be able to classify them automatically so that we remove them from our pool of anomaly filters. And and this is just for a given asset. We looked at 60 events. We were able to go in and identify the incomplete events, take them out. The remaining pool of events, which is actually the one we want to look at, we were able to identify which of these have anomalies, and we found in this case 17 of 60. The remaining we classified as normal. And more importantly, we ranked events in order of anomalies, so that when somebody comes in and they want to look at what really is anomalous and to what degree is it anomalous, you have a ranked list so that you can pay attention to events that really require attention. In addition, Spark Predict allows you to compare things across events. So you can compare events which happened in time. So I could look at the last 5 transient events for a particular asset. I could look at on a particular day how 5 assets stacked up for the same event. So all those combinations of comparisons are available. And we also have support for anomaly detection of sharp center line plots, which you will in subsequent. In terms of insights, what we are getting to is trying to drill down exactly what vibration analysts should spend their time. What are the events they should really look at? What are the baselines for those assets? We want to provide them a way to view degradation across assets or within a particular asset to see how it's happening over time. What are the features that are moving from a normal state to a failed state, and at what rate? And we provide the behavior for each asset independently. So a particular turbine might have a different normal state of operation from a turbine which is located in the same bank. And our models capture that so that you are not looking at deviation from just the manufacturer's specifications, but deviations from a normal state that has been observed over the line. And as new data comes in, we can retrain the model. So now your new normal, instead of, let's say, 30 events at the start of the project, we'll go to 50 events somewhere down the line, 100 and 200 and so on. So the normal continuously goes through. And the plot here is a sharp center line plot where you can see actually, for folks at the back might not be as clear, but you can see the blue line which actually shows how the shaft moves for an actual startup. The red line shows the normal motion over time, and the yellow area shows actually the bounce of it. So using those, you can actually look at bounce. And Keith actually will go into further detail in the demo.
Excellent. Yeah, let's jump into a demo, guys. So I will go ahead and say, I apologize. I was having spotty internet this morning, so I decided to go ahead and record a video. And I'll walk through the video that I recorded in my moments of internet. Let's see. Here we go. So we'll start here. So walking in, this is going to be the very first thing. So say it's a Monday morning, your vibration analyst walks into the office. This is the first thing he's going to see when he pulls up his computer. It's a nice dashboard that has already used a lot of smart cognition algorithms to pre-filter data that's going on that happened over the weekend. So he walks in, he can look at this dashboard, he can filter through all of his assets, whether it be globally or just at a specific site. He can take a look at what type of event, so say he's looking at turbines again, so startups, coast downs, whatever it may be. And then he can go and prioritize those by actual chance, so if the asset's at risk or not. So you notice you can walk through those, see kind of if they're at risk, etc. And one thing I want to call out is in developing Spark Predict, we worked with vibration analysts. So this isn't the data scientists coming in and saying, hey, look how cool data science is for vibration analysts. It's vibration analysts and data scientists coming together to create a product that's relevant for everybody. And so say your vibration analyst would click through and take a look at what's going on there. So first thing you can see on that left side is you have the ability to filter through almost every single channel within a specific event that he drilled down into. So you can look at Bode plots, you can look at shaft centerline plots, you can look at speed profiles, and then for each individual channel, you can sort through different columns of data that you would have. So say you wanted to look at one specific channel, you have the ability to sort for that. You can sort for different features that you're reading through on each channel. You can also sort for the overall anomaly count. So we're going to look at the plot you see the most anomalous. So you can see really quickly here, as you drag it all the way out to the max RPM, why there's so many anomalies, and those are called out in pink. So the algorithm automatically looks at data, recognizes how far it is from normal, has flagged it as anomalous, and said this is an asset that's at risk. And this is the very first thing, it only took a few seconds of his day. As he drills into it, he can actually look on a line-by-line basis, so per RPM, say on a Bode plot, what does he care about? So what are the actual 3 sigmas here, and how is this point anomalous? And you can do it for both the phase and the magnitude plot. This is just one example with as far as Bodes go. You can also, on-the-fly customization of plots if you're trying to create a printout for your boss really quickly, pretty easy to do. And you can do exact compares at points that look specifically odd. Now another thing, so this is one event, meaning this is a single startup. But what you really care about is what happens over all startups, or maybe there's just another specific startup that you want to compare to. We've added that functionality in as well. So say you wanted to compare to just one other startup, you can pull that down from the drop-down menu and visualize what that looks like. And you can clearly see in that phase plot that there's a significant shift from startup number 1 being that blue line and startup number 2 being that green line, which is why it was flagged as anomalous. And you do this for every channel. So each individual item that you see, so each row on that left side has its own specific set of plots and data. They are just reorganized so that when a vibration analyst goes to look at it, the most prioritized ones are at the top, and that's completely configurable. So another thing we're calling out that Sumant had talked about is our shaft centerline plot. So I'm going to pause it here really quickly. So if you want to look at a shaft centerline plot, you see that we've taken in the data, and this is very similar to what you would see in Insight CM. We're basically taking data from there and revisualizing it with, I guess, additional analysis on top. You can see there's 3 sigma bounds that we're calling out, so identifying different anomalies that could occur, as well as what the normal for that particular plot would be. And if you want to, everything is configurable, so you just want to get a feel for the shape of that particular motion. So what the shaft is actually doing on that startup, you can do that. Now, I like to call it, this is the world of big data. So we've looked at a single event. This is, I guess, an industry in condition monitoring where there are millions of events that go on. So it's really difficult for an individual analyst or even a team of analysts to catch every event and capture all anomalous behavior. The real benefit that something like this is bringing is not only performing analysis and filtering of data that's perfectly normal, but it can then highlight what they should look at. It is an augmentation of existing systems, not something that comes in and replaces everything we have. So, everybody cool with the demo? I'm gonna keep moving at this point. I want to give a quick overview as far as how we work with NI tools. Let me see if I can work my computer. All right. So, how our stuff actually works with NI. I know we've talked about being a partner. You might have seen on the slide we work with TDMS, work with Insight CM. So what does that actually look like? I want to reiterate this in that we are not an Insight CM replacement. We are not a data acquisition company. We are a cognitive computing, machine learning, data analysis company. So our partnership with Insight CM is taking data, or National Instruments is being able to take that data and provide another level of complexity with regards to, or another level of understanding, per se, on top of that. So what you're going to get is a seamless integration with existing systems, and that's something that we'll work very hard on. If you are, how many of you guys are familiar with Insight CM in regards to the overall architecture? So we plug in 2 real places. So there's through the server, through an existing historian, so that's where the streaming will come into play. So streaming data from your assets. And then secondarily, some of the visual tools. We're working on plugging in with the Data Explorer as well. Now, just to kind of visualize how this relationship works again. So we have acquisition, data logging, and then publishing all this data to IT. That's where Spark Predict and Spark Cognition software comes in. We are not going to sell sensors. We are not going to work with you on data acquisition. That's something, me being an ex-NI employee, I am very familiar with how good NI is at these things. So that's why we really value this partnership. Thank you, guys. I suppose we have, how much, about 20 minutes?
Yeah, we have 20 minutes for the other slides.
Want to jump in?
Yeah.
Okay, so I guess let's start with questions first. If anybody has any pressing questions on what we have right now, we have a bunch of appendix slides that we kind of tagged on at the end with other case studies, etc.
Have you done any modeling, predictive modeling technologies outside of vibration, or right now is the highest basic we've just been taking a look at vibration data, and what's your ability to actually correlate multiple?
So that's a great question. So vibration is one of the applications that we have addressed, but we are not really limited to a particular application. We have worked with rotating equipment without having vibration data. So pumps of different kinds, which are used in the oil and gas industry, also used in the industry. But these might be pumps which just aren't at the same level of cost and criticality as gas turbines really have those sensors. And we have had great results with those as well, because the way the application works is similar. In terms of vibrations, you might have data at an FFT level that you can analyze, you can get signatures. With data, with other applications where you do not have vibration data, you would have pressure, temperature, current, voltage going into the system, all these different parameters, and you apply the same algorithms with similar models, try to detect the state of the system and the predictive signature, and predict failures for those assets as well. So vibration data is not a requirement.
How many times does mean, obviously it always depends on the subtlety of the signature, but how many times does an event or a failure or whatever have to happen before it is able to consistently see it come?
Good question. I mean, it depends. I mean, it depends on the state of the system. It depends on how tightly the class of failures is bound together to its centroid. But in our experience, in most cases, with a bunch of assets, what we have seen is that we have 10 to 15 failures of a particular kind. Those have been a good enough number for us to develop a signature that we can come for.
Do you have to have classification of data prior to? It's just basically looking for this is different than this. These are like all the same. You know, which of these things don't belong together? But then, at that point, then it is the subject matter expert supposed to identify what that is, to tag that information, and then that becomes a pattern that's used for. If you have that information going in, so we know that these sets are bad and we know that these sets are good, would that basically speed the system up?
Yeah, another great question. So let me break it down. So we can work with what you have described are basically supervised learning and unsupervised learning. We can work very well with unsupervised learning, which is where you give us a bunch of data. We can figure out the normal. We can talk to you. We are not constrained from talking to the SMEs, but we can very quickly identify what the normal is. That's the key part of the analysis. And then we can see what are the deviations from the normal, like we said, what are the different failure classes and so on. So that's in the field of unsupervised learning. What can work even better is supervised learning, where we get not only the data, but more input from the SMEs about how the system is working. So they could tell us what is normal, what is a failure, what are the different kinds of failures, when they happen in a particular data set. So now we know more about the system, we know what's happening. But what we have seen is that most of the data is usually collected forensically. So it's not that the data is, the state data is hard to get, but it's usually when failures have happened, somebody has gone in and collected that data and been able to say, okay, this is a failure, this was a short or a probe or something else, and then they put that label in. So we can use those labels also, and now we can actually be even more specific about what kind of failure signals we are seeing. Whether short has a longer predictive signature than probe. So you have 10 days of warning versus 5. So all these things we can get to quicker with supervised learning. But supervised labeled data is not always available. So we will work with the data. Does that answer your question?
To piggyback on that, just to provide, I guess, a clear-cut example of supervised versus unsupervised learning. How many of you guys have ever listened to Pandora? So the music station. I know Spotify is like the bigger thing. I still listen to Pandora. But there's a thumbs up, thumbs down button on Pandora that will make or kind of change your playlist based on what you put thumbs up and thumbs down for. That is supervised learning. You were giving the input, yes, I like this song. So it is changing what it's doing to actually create a playlist that is more optimized for you. That's a very simple example of it, but something that a lot of people can understand.
How does sampling frequency impact the accuracy of monitoring? We have clients where we're doing both online continuous monitoring of data, and we also have a very large client presence, so we want to do route-based data. So obviously with the route-based data, you don't have nearly the number of sampling points. So how does that impact the accuracy of the model and the models building perform?
So sampling is important. I mean, it would be first level observation that the better data you have, the better your predictions, the better your analysis. It also depends. We have seen on things like the lifetime of that assets or the mean time between failures, depending on what the repair versus replace characteristics are. And the sampling frequency is related to that. So for transformers such as for transformers which don't fail as often, we could have data which is collected over days and it still works. For transient events, we want to collect it much more frequently. For PSPs which have a life of about a year, you want to collect them at minutes. So usually we have seen 10 to 15 minutes apart. So that's relation to the MTTL. In terms of sampling itself, what our algorithms do is is we not only look at first order data, but we can create higher order features out of it. So that can, in many cases, or I would say in most cases, help us get over those infrequent sampling issues. Not always, because there could be a data set which is just not capturing things. But in most cases, algorithms and IT such as Spark IPR helps us get over those.
Plus the trick there is across multiple comparable assets. All of a sudden, the aggregate data set is bigger than the data set itself.
One thing to keep in mind for something like that is that there is going to be a trade-off. So naturally, you want to say more data is going to be better for everything. There's also processing power to be considered. So we are not a computer company and do not make computers. Therefore, there's going to be a high level of analysis, and the more data you have, the more processing that's going to be involved. So if you're throwing terabytes of data at something that only fails once every 80 years, it might be considered overkill. So it's a balance to sort out on a kind of per asset basis, as Sumant mentioned.
Yeah, and as compute becomes cheaper, as storage becomes cheaper, bandwidth becomes cheaper, though not at the same rate. There's also IT problems that we can solve on the IT side to make sure that the data that we need is available at the place we can analyze it at. So there's that different way to look at the problem as well. Any more questions? Well, thanks for your time.
Thank you, guys.
So you still going to another session?
No,